What does yours say?
Oh no! It says out of order.
I wonder how long it's been like that.
I don't know. What's yours says?
Oh, it's just got a picture of me, and I've hearted a few of the eyes and
Yeah,
stuff.
yeah, you have. There's a heart for the symbol. It's all pink.
It's all pink because not many people do that, so
Oh,
I'm special.
That's lovely.
And
Is it film? We should get onto
get on to
chemistry or something.
yeah. So part 2 is module 2 of Unit 1's
It is.
F321 paper.
And it starts with ionic bonding.
Yes, because we mentioned at the end of part 1 the different types of bonding. We're now going to go through them.
We are. So ionic bonding is bonding between ions, and this one isn't the sherry kind.
Okay, so no, it's not ionic bond. That's the title.
Yep. And these bonds are taken, not shared.
Yes, so between ions.
So mentioned before, it's when that side of the periodic table bonds with that side of the periodic table. A gas with a non-gas.
A gas with a non-gas, yeah. And that makes your ions. So how do you know what ions things make?
Well, that's a good question, Wayne. Some you just have to know what they are, and then you can work out the others.
Yes. So you ignore the noble gases because they don't form ions.
They don't form an ion.
The one before it forms 1 minus, the one before that 2 minus, and then 3 minus.
So they sort of form the fastest way to get to that.
Yeah. Because that forming a 1 minus, a 2 minus, and a 3 minus is much better than forming a 5 plus, a 6 plus, and a 7 plus.
Yeah.
Likewise, on the other side, we actually ignore these ones for the second, the D.
They do weird things, but they can form 1 plus, because that gets them straight to there, or 2 plus.
Or 3
3
plus.
plus.
So it's the groups, not this middle way.
Yeah, the 4, 5 change.
Yeah, carbon you don't really do at this stage.
No.
It does special things which you do all about in Unit 2, but we don't really touch on it in terms of ionic bonding here.
No, and some of them form different ions, but you can work it out from the ions you know.
Yes.
So let's go through some. Okay. So some ions you should know are hydrogen.
Yeah.
That's
Hydrogen
1 plus.
is plus. H plus.
You should know, like Wayne said, all the group 1 elements are 1 plus. Or
Yeah.
2
So
or
you
2
can have
plus.
like lithium plus and all that.
Yep.
Mg2 plus often comes up.
Yeah.
And Al3 plus, the same as B3 plus, which is
Yeah.
boron.
And you need to know a few negative ones. So we have oxygen, so O2 minus.
Or O2 minus. Chlorine and all of the ones down there.
Yeah, all of the halogens with 1 minus ions.
And you can have nitrogen, which is -3. That's how
Yeah.
it forms the NH3, because there's 3 lots of plus to get out the -3.
Yeah, but you don't just have elements just floating about. You have molecules and compounds.
Yes, such as, we'll go with the N example, if you have 4 hydrogens to 1 N, overall, because there's 3 minus there, and each one of the 4 hydrogens would be a plus, that would make a 1 plus ion, so it's NH4 plus.
Yeah, which is ammonium.
Ammonium, yeah, that's the name.
That's one that's useful to know, so that's got quite a bit later on.
So let's actually get on to drawing some of these, such
Yeah.
as salt is a very, very common one, NaCl.
Yeah, it is. So when you draw on ionic bonds, this is something you do at GCSE.
Yeah.
It's not the overlapping circles, it's the 2 separate ones in the square boxes. Yeah, in each one of them, one of the outer electrons, and one of the outer electrons will be X's or something, the other one will be dots,
Yeah,
or
so it's
a different
always referred
shape.
to as the dot and cross diagrams.
Yep.
So Na forms a plus because it's in group 1.
It is group 1. So that means it ends up having nothing in its outer shell.
Yes. Alternative in the marking in terms of your exam, you could do all 8 for the previous shell.
Yeah, but you
it's
don't
easy
need
just
to,
to do
so
none.
but I wouldn't. And then we have that. Oh, okay, sure. We'll do the next one next.
Oh, yeah.
We have a plus on
Sorry.
top of this.
Yep.
Which shows it's charged. It's an ion. And then we see Cl, which has all its normal,
Yep. So it has
things.
7. 1, 2, 3, 4.
and then it has the one from Na, which is taken.
So
Which
because
could be
it's
a-
from the different thing, you
you
use
get
the
the
dot. And
And that gives it a minus charge. So it's got an extra electron and then a negative. Yeah. You know, like that.
that's that.
Done.
You could have magnesium chloride, because that's got 2 chlorines, because Mg is 2 plus, so you get MgCl2.
Now what you do here, like you do there, except you have 2 of these.
Yep.
So often you'll have maybe like half the size or something, just add them next to them, and they work in the same way. This would be a 2 plus, and each of these would be a minus.
So that would just be empty. That would be, each chlorine would be exactly like that, because
Yeah.
each one has only gained 1. That's why there's 2 of them.
And then they
each minus.
both have a minus, and that would have a 2 plus, because that's the one it forms. That's stated there.
Yeah, I'm not going to draw them all on again, but it's just to demonstrate. I thought that'd be a useful example.
Yeah.
And as Triv said, if there's one you don't know, something that might change the ionic forms, it's
Yeah.
often given with stuff you know that are constant, like oxygen or hydrogen.
Yeah.
And
You can work out what the other one would have been.
yeah, if it doesn't have a charge on the ion like this one does, you know, it'll all add up to 0. So you know,
Yeah.
if that's 2 minus, it would have to be a 2 plus. So if there's other stuff, you can
Yeah.
work.
Compounds always add up to 0. Something we should add when they're things on their own, they have no charge.
Oh, yeah, you could do that. Yeah.
Yeah.
So stuff like.
So if you had an equation, like things like its own, Mg with
Oxygen.
oxygen.
No, magnesium on its own is just solid, it's not an ion.
Yeah.
Oxygen on its own, O2, as you know, isn't an ion.
Yeah. So these would just be, they wouldn't have a charge there.
But because
then,
it's a metal reacting with a gas, so a gas and a non-gas,
yeah.
it will
Makes an
form
ionic.
an ionic thing, and that's
Is
Mg
it,
is
yeah?
2 plus, O is 2 minus, so it's MgO.
Yeah.
Magnesium
You could
oxide.
balance it like that.
Yeah.
But yeah. And then they would be different. That'd be 2 plus, that'd be 2 minus.
And the same with NaCO, you could react sodium with chlorine on their own,
Yeah.
there would just be sodium and chlorine. So yeah,
Yeah.
that's ionic bonding. So
ionic bonding.
we should get on to covalent bonding, I think is next.
Alright. Covalent bonding.
Yeah, again, familiar from GCSE. Not really any advancement, but there's a few things
No.
you have to know.
There's a few basic things between gases and gases. And they go good.
Yep.
Sharing stuff.
So,
So nothing crosses will overlap and stuff.
it's a shared pair is a note to make.
It is shared pair of electrons. And one electron is generally supplied by each side. But not always.
Yes, there's something like Cl2, you don't draw the rectangle-y bits, you do one chlorine, which will overlap with another chlorine.
And in the middle there'll be this shared pair. One will be from one side and one will be from another side.
Then the rest.
And the rest will go round like normal.
So overall, they all have the 8 in their octet.
They do. They all fill out their octet, which is what things want.
Same with hydrogen, I'm not going to draw it again, except that there's only 2 electrons in the outer shell.
Yeah, but it fills the outer shell because S only can fit 2.
And it's as simple as that.
Yeah.
Oxygen, all of that work the same way. The next thing you got to know, it's not always a single bond like this.
No, you get something called double bonds or dative covalent bonds.
And you can even get triple bonds.
You can. They're bonkers.
Yes.
Yes.
Examples is the oxygen I just mentioned. That's why I didn't put it up with these ones, is because it's actually a double covalent bond, not
It
that.
is.
Sort of means twice as many things are shared, as each
Yeah.
one will give 2
2.
electrons.
Yeah.
So,
So I'm going to draw there. One side, oxygen, the other side. And you just have lots in the middle.
circle, circle, cross, cross, and then so on.
And then fill out the rest.
And then N2 has triple bonds.
Yeah.
Which is the same,
Same thing.
but 3.
And this is how we show them in the circle swap sides.
Yeah, okay.
But if you were to talk about them, you'd write it. The O would be a double bond, so that'd be like that.
N would be triple.
N would be triple, so that'd be 3 lines. And all bonds you similar for just a single.
Would be single. And because carbon can have 4, the CO2, the carbon's in the middle, it forms 2 double bonds either side.
Yeah.
Because the oxygen needs to have 2 things shared. Oxygen doesn't always form a double bond like this, it just needs to have 2. So something
Yeah.
like water
Yeah.
has 2 singles, which is sort of makes the equivalent.
It does. And lone pairs, which we'll go on to a bit later.
Yes. So, in fact, let's go on to that now. If we
Yeah.
do the example of the NH4 plus ion.
Alright.
Rub some of this out, you can draw up the ion if you want.
Okay, so like Wayne said, we
Okay,
have
so
NH4. I'll jump over this side. NH4, the N has 5 things that can bond with from there.
Because it's in group 5.
So ammonia is what it's normally bonded to, so it has hydrogen on each one. So it's got
Sometimes it
another
bonds
pair.
to another hydrogen to make the
Yeah.
NH4 plus.
But it provides both of the electrons.
Yes.
So it might have a thing. It isn't often drawn like this.
Yeah, that isn't a double bond. It's just to
No,
represent that
it's
both
both
the
electrons.
electrons come from the nitrogen. So,
Often you probably draw it with let's do the dot and cross.
okay, that makes more sense.
That makes more sense.
Be like this. The hydrogens do what they normally do. They give
one.
The nitrogen gives 1.
And here the nitrogen has 2. And it basically does that.
Yep.
It provides both of them.
So that means the hydrogen, the one that it would donate, is lost. That makes
Yeah.
your plus. So it's actually in the ionic form
It
like
is in the
this,
ionic
because it's an ion, but it has covalent bonding.
It does, and that's a dative covalent bond.
That part. And that's the only thing that's really new above GCSE.
It
is
is,
the dative covalent bond, which you need to know.
Yeah, lone pairs go into a lot more later because it changes the shape of things.
Yes. In fact, we can crack onto that now. That's the next bit.
Okay.
No, there's no more covalent bonds to do.
Alright,
Right. Shapes.
Shapes. I'm a triangle. Shapes.
So, electrons repel, as you know.
They do, and that makes them do things.
It depends on the amount of electrons you have in an area to how much
Yeah.
it repels and how
So,
condensed this electronegative part is.
yeah, so you have stuff like you have double bonds, single bonds, lone pairs, all this jazz, and they repel at different amounts.
Which give it certain angles, certain shapes in three-dimensional space.
So you need to know lots of shapes and the examples of the shapes and why they make the shape.
So, first, let's start with a simple one, BF3.
Alright, so boron has 3 electrons in its outer shell, and well, F wants to to all of those.
And you have 3 of them.
You do. So it's going to make some sort of triangle-like thing. So you can draw it like this, and I'll draw it over here like that.
I'm not going to bother with all the electrons because you should know what happens.
Yeah.
This is
Sort of
actually
split like that.
This is actually all in one plane, so
It
this
is, it's
could
all
be
flat.
as the board is, like this.
Yeah,
So, as it makes a circle all the way around,
It does.
you should be able to see the angle.
360 in total, so that's 120 is the bond angle.
And you will be expected to be able to quote all of the shapes that are in the book at any point in the exam.
Yeah, you got to know why as well. It's because they're all the same, so they all
repel
equally.
equally.
Yeah, so that's, and what is that called, Wayne?
It's a special name,
It
and
does.
it's called trigonal, sort of like a triangle.
Yeah.
Trigonal. Planar to indicate it's in one
Yeah,
plane.
and a triangle, because there's 3 bonds and it's flat, and planar because it's in a plane. Does make sense.
Does make sense. Next we should have tetrahedral, where there's 4 bonds.
Yeah.
Something like CH4. Should we go
So
over
that's
here?
CH4, yeah, so you do the circle again, and I'll do...
Okay.
So, like tetrahedral suggests, it sort of makes a square.
Yeah. Except it doesn't quite make a square. These aren't quite 90 degrees, because it's in 3-dimensional space. They can get
Yeah.
further apart than 90 degrees in 3D. And the bond angle, you have to remember it, is going to be 109.5.
It is.
They normally in the exam will allow you to be between something like 108 and 110 somewhere.
Yeah,
Well, I
but
would
if
remember
you
the
just quote the
actual
value, that's pretty swish.
They might be really strict, like there is some where they expect the exact answer sometimes to give you a
Yeah.
bit of leeway, but I would just remember it.
And this one isn't in a plane, is it?
No, because
So
if it
you-
was in a plane it would be a square, that would be 90.
degrees.
To
So you
3D.
have markings on it.
Yes. we
And one
do.
of the memes goes through the page. This was sort of flat. This one, is it this one?
Yeah, that one means going into it, and you could have dashing triangles like this, something like that.
It means coming towards you.
So you'd look at that and think these two are where the board is, this one's
Yeah.
actually sticking out towards you, that one's going into the board,
Yeah,
and tetrahedral.
and that's the name. There's quite a few of these. And I
Yeah.
want sort of like the triangle thing is pyramidal.
Yes, so first I'll give you a chance just to look at this because I'm about to rub off BF3.
Alright. There it is. Right.
So what one did you say, sorry?
I said pyramidal.
Pyramidal, okay, so NH3.
Yeah.
Now this is where things start to get you a few more marking points.
Yeah, it gets a bit more exciting. You should remember nitrogen has 5 outer electrons, only 3 are bonded. That means there's a lone pair. So I'll do what we did with before.
Yep, okay.
So there's this lone pair. I mentioned before that some bonds and stuff repel more,
Yeah.
Lone pairs are one of these. They repel much
You
more.
sort of
than
think the
normal
two
pairs.
electrons being in one place, really close together, like a ball of negative, if you will. Whereas these are sort of spread out negative, as you could think of it like that.
So that would push these round away.
So it wouldn't be like this where they're all equal. It
No.
wouldn't be 109.5. You can imagine it's going to be slightly smaller.
Yeah.
But again, it's in 3 dimensions. So awkward number, but you've got to remember it. 107 degrees.
Yes. Now, every time you add a lone pair, it just goes down in a similar amount. It starts at 109.5, and with every lone pair, it goes down by 2.5.
So the next example is water, which has 2 lone pairs.
It is, and that'd be 104.5.
We'll get onto that in a second. First,
Yeah.
I'll write up the name.
Which is pyramidal, because it's sort of like a pyramid.
Yeah, with sort of the point at the top and then spread out
Yeah.
for the 3 bases. Pyramidal. Again, I'll give you the chance to quickly pause and copy this down before I rub it out. I'm rubbing out
Yeah.
that side.
Okay.
Right, awesome. So,
Right.
water, H2O.
Yeah. Mentioned again, this one has 2 lone pairs.
And we'll draw it.
So there's a lone pair here, and a lone pair here. That pushes these a lot closer together.
And as Triv said, everyone's 2.5. I've already said the angle, but I'll say it again.
Yep.
104.5 degrees.
Yeah.
And
It's
you've
got
got
a name.
that. It has.
It's called non-linear because it's not flat. Or some people call it a bentacular or something.
Yeah, there is other names you can learn, and they will be accepted
They'll
in
be
the exam.
accepted.
I just remember that once it's
Yeah,
nice and easy.
non-linear is easier than the other one.
Give you a chance to pause. I'm going to rub this one out. There we
Yeah.
go.
So if we have non-linear,
There must be a
there
linear.
must be a linear, and that's when stuff is flat.
Yeah, it's linear, like a linear graph, straight
Yeah,
line.
like straight line.
And it's
So
another one you're
stuff like-
familiar with, like H2O,
Yeah, but like
CO2.
CO2. Mentioned before, there's 2 double bonds, but because they're both the same, they both repel equally.
Yep.
But both quite a lot.
And because it's going to be in one plane, because they repel equally,
Yep, so that's
180.
180 degrees. It's quite a big bond angle.
and that's
Linear.
And there is one final example.
There is, and I think they only really use one example for it.
Yes, and that's SF6 with an expanded octet.
Yes, and that's when there's lots of octets throughout. I'll wrap this up. And yeah, that's called octahedral.
Yes, and it's weird. It's really hard to draw how it works.
Yeah.
This one's a little bit more logical. We'll give it a go in a second when Triv's drawn it up in his form.
Yeah.
But yeah, SF6, we'll do the usual. I'll draw it, and Triv will draw it.
So sulfur has 6 bonds.
1, 2,
It's sort of
3, 4,
like
5, 6, and these are all F.
all equally spread out. But it's not linear either.
No,
not in a
not
plane.
planar, it's all 3D. And it's really, really hard to draw. Some of
Yeah.
these go in, like that one might do that. There'll be 2 that go in.
Yeah, and there'll be 2 that sort of go out.
Yeah. And if you think of an octahedral dice, an 8-sided dice,
Yeah,
Those 8
between
sides.
it's sort of there'll be 90 degrees between them. Sort of hard to imagine.
yeah, that bonds in 3 dimensions to that. It
Yeah.
makes like a triangle, and they all make their own triangle, like an octahedral dice, basically.
Yeah.
And 90 degrees, you got to know.
Yeah, 90 degrees is the bond angle.
Yeah.
Yeah, and it's called octahedral.
I forgot the name, yeah.
Yeah.
Octahedral. Because 8 sides.
Yeah. And this is the only. They like quoting this example though because it is sort of hard to picture and understand, but you just have to know stuff about it.
I just remember the names and the angles rather
Yeah.
than thinking about them each time. I like to remember all of them.
Yeah, but you can know all the stuff and work it out, but it is better just to know it off the bat.
And any of them can be asked to be quoted, and
They
that
can.
is shapes.
And that is shapes.
So,
Now we're on to
lone pairs repel greater than bonded pairs, basically.
Yeah.
That's the essential point. So now we're on to electronegativity and polarity.
yeah. Let's crack on. Hello.
Electronegativity and polarity, new above GCSE.
Yeah, very new and quite a few new ideas. But why does it happen?
Well, it's all to do with the idea that some atoms can take electrons more easily than others because of the number of protons and the nuclear charge.
Yeah, we can sort of show this with a periodic table. So draw one up.
Yep, you're not expected to remember any of the values that are in the book, just roughly
No, just
what happens.
the trend. So basically, he's mad.
Yep.
He has the highest, and that's fluorine, has the highest electronegativity, and that's because it has the least shielding, relatively, but the highest nuclear charge. And there,
It has the least.
yeah, and the lowest nuclear charge.
Yeah.
And it all follows that trend as it goes across and up, has less shielding and more protons. They pull stuff more.
So this across isn't quite what you up is logical because of the less shielding, but across isn't quite what you think.
No.
Because you're adding an extra proton each time, but there isn't a whole new shell. They actually get closer
Yeah,
together.
they get
Atomic
really,
radius
that's
gets
a
smaller.
really small atom.
Yes.
Tiny, it has a huge pull.
And that can react with everything. Noble gases don't react except from krypton and xenon, which can be prepared, but it's quite difficult.
It's very difficult, but because they have a full octet already, they don't care.
Yeah. So these are all grey, and there's some across the bottom that are grey because they haven't been prepared, and normally they can't be
measured yet.
That's electronegativity, and
Yeah.
we could represent this with dipoles.
Yeah, and dipoles sort of. I'll draw one up first. So if you had fluorine and it bonded to carbon. Okay.
Fluorine's the most electronegative, you should know. That will become delta minus, which means slightly negative. It can attract the electrons more towards itself than the carbon can to itself.
Yeah, so what ends up happening is this has more than its unfair share of the charge. And that means more electrons, it's more negative on this side, forces it to positive. That way around.
Which is above GCSE, so GCSE that's a covalent bond. Now that's a covalent bond, but it's slightly to this side.
And here's where the shapes happen and it gets a bit more complicated.
Yes. And it's because of this that we get some special types of forces, and we do. Dipoles, which is what this is.
Yep, and something called van der Waals.
Yes. So let's go through that now.
Alright.
I'll rub off this periodic table.
It's very beautiful, and it took us hours to prepare it.
So bad.
Show you shapes, it's fine.
So there's two different types of forces that are new.
Yes, these are intermolecular forces.
Yes, they both are. Intermolecular means
Between stuff.
yeah. So it's not the covalent or ionic or metallic. It's within that. So first we have dipole to dipole interactions.
Yeah, and this is sort of what we mentioned there.
Yes, except that one isn't a good example. And let's explain why now.
Alright.
If we had something like HCl, that's in a dipole to dipole. And then we have van der Waals.
Remember it's German, so W is like a V, but you know it's a W, so you like spelling.
Yeah. And CH was in that one. So what's the difference? What's going on? Why is this and this is van der Waals? What's the difference?
Well, Wayne, it's to do with the different electronegativity differences.
Yes. In this one, it's permanent. There's always going to be a dipole.
Yeah, because there is a really strong difference. It's basically like a north and south pole, sort of, in the molecule.
Whereas in this one, each C to H does have
A
dipole.
Yeah, a little bit of a difference.
It's symmetrical, so they're said to cancel out.
Yeah.
So it makes sort of minimal difference. And so the way we get these forces is by the oscillations of particles causing instantaneous dipoles that don't stay there like
there's
this
a sort of appear and they're gone and they appear and they're gone, but they're all always there.
And in the book it gives you a little table of relative strength. So ionic and covalent are about 1,000 strength. You don't know what the unit is. This will be about 10 and van der Waals will be about 1.
Yeah, it's not very high.
So that's the difference between these. If it's permanent, it's dipole to dipole. If these do have dipoles but they cancel, it's van der Waals.
Yeah. And this affects boiling points.
Yeah. So things that have just van der Waals are said to be simple molecular.
And they'll be gases generally because their boiling point is so low.
Yep. Whereas covalent and ionic bonded things and metallic have such high boiling
They're
points.
often solids or liquids. Yeah.
And often in questions you might be asked to compare something like potassium bromide to water and magnesium. And you'd have to say the different
Different types of bonds and why they're different amount of energy to break the bonds, that's why it's a higher boiling point. this
all
sort of
that
thing.
sort of stuff.
All that jazz.
So that's all to do with electronegativity and polarity.
Yeah.
And then the new intermolecular forces.
There is more.
Hydrogen bonding, which is in fact above this, and I think in the table it says a relative strength of 50.
Yeah.
We go on to that in part 3.
Yeah.
So let's go on to that right now.
Let's go on to it now.
I'll see you there.